gonna close this one. All right, so for those of you following in the hands-on, basically the way that we've set up this training is, there's a lot of content that we're covering. We wanted it to be, somewhat self-paced, or at least like if you don't follow it live, that, there's still resources for you to look at. So basically everything I'm going to cover is in this README for the GitHub. So um, where we're actually going to start is in this single GPU performance profiling and optimization section. Wish this. The other thing is that this GitHub thing likes leaving this like app a white space here, which is I don't know what size it is. Okay, anyway. Um, so the first bit we're going to cover is like how we would profile. And as part of this training, we've tried to make things sort of as streamlined and as easy as possible. So um the first we ran, we ran this before. I was gonna say before the break, we had people run this short config, right? Um, so you should be able to see, like, I ran it before the break too here. Oh, that's very laggy. Um, so I have like an output that just looks like that. Why is this? Oof. I'm like having crazy lag on the yeah,
Hopefully Jupiter's not suffering.
there it goes. Okay. It could also be I'm like I should have disconnected from my VPN before I did this. But we can see something like, these are taking something like 54 seconds. We're basically just looking at the time taken for the epics, right? So the first thing we're going to want to do in the hands-on is learn how to use Nsight systems. And so we're going to have everybody run this command here to generate a profile on Perlmutter. Basically, you're just going to run the same command you did before, this sbatch-n1-t20 command. So, but we're going to add this like enable profiling one, profile output baseline, like environment variable beforehand.
Can you zoom in any more on that left window, the README?
Yeah. I mean, that
Oh, there
works.
you go.
So we're going to be running like this command. Sorry, it's like I need to scroll it, but enable profiling one, profile output equals baseline. And so to elaborate on what that's actually doing, let's go ahead. If we look at, is the text in the terminal big enough, Steve?
I don't know.
It's just hard to look at. Okay. Maybe I should just do like I'll just do separate tabs. Let's have that. So I can at least. So what the enable profiling is doing is like these are just arguments that we added to the submission script. So this is inside submit.sh. We see that the profile command is what's actually being launched before. And if you remember from the slides, it's basically this NSYS profile, NSYS args are what they've defined here, dash O NSYS output. So these are controlled by if enable profiling equals one, and then the NSYS output is profile output, the flag there. So all that command here is doing is running NSYS for you. So basically, if you copy this and run it, it should start generating a profile. I will show um, or maybe it will. Oh, okay.
It just took a little bit.
So I'll tail that for now, but in a different terminal, I'll kind of for now just kind of give a quick overview of what that enabled. So if we look at train.py, so in our editor, Basically, if you search for something like NVTX, you'll see all the places that we've added these NVTX ranges. So kind of like in the slides, we had, NVTX range push, step data copy in. There's pops, NVTX range push forward, range push optimizer, in various places. The other thing that we didn't really cover in the slides that we're using here is this Torch CUDA profiler start and stop calls on Epic 3. So it can sometimes be useful to only profile like a certain segment of your run. So like you might start it from Epic 0, but you want to, start the profiler maybe after a few steps of run. You can use Torch CUDA profiler start and stop to tell NSYS when to like begin and end profiling. So it's just a useful feature there. So that's basically all we've added in terms of NVTX to this model, to the model script. So that's currently running. In order to save some time, so basically this will run. It's going to take a little while because this is our slowest possible config. We've actually added the NSYS profiles to the GitHub for you that are already generated to make it a little bit faster. So inside the sample NSYS profiles folder, there's actually a bunch of Nsight profiles that were already pre-generated that you can look at while this runs. So it looks like this. Oh, I was actually looking at the wrong. I was tailing the wrong output because I was surprised that this was done. But we can let this run. But while everyone's waiting for that to run, I'm actually just going to end up opening this baseline NSYS rep file on my own computer and start walking through that. So these files are the files that get generated. I don't know why this is. It keeps getting stuck.
Doesn't want to control C out of it.
Yeah, no, I don't. Am I the only one experiencing this, or is it?
So you might want a new terminal.
Yeah. Well, okay. So that should be running, and then as it runs, maybe I'll just view it instead of tail. Maybe tail's not. Yeah, so this is still running, which we can also see of like an SQ dash me. It's currently running. I think that these should be dumped in, like the profiles will get dumped in logs.
So that was not, I don't think that one's enabling the profiler.
Are you talking to me, Steve?
Logic.
Okay.
But they'll just maybe
I'll just mute the room. You can carry on, Josh.
Okay, so let's go ahead. Yeah, that's fine. Okay, so can people? Okay, it looks like I can kind of see my screen in the background there, so I can see that. Wow, this is very small. So what I've actually done here is I've actually git cloned the repository to my own computer, and I've opened up the baseline Nsight NSYS rep to my computer here. So this is actually what it looks like when you open it up. I don't know if people are able to see this, but what the Nsight Systems program that you installed on your own computer is like a local program that you can use to open up these NSYS rep files that you've generated on a remote system. So in this case, I'm looking at like the baseline NSYS rep. And so as I've showed, there's this like upper section here, like basically from this row to this row, that are like the CPU rows of the profile. And then this bottom section here is the GPU section. So this is showing a profile over what looks like maybe 20 steps. Each of these gray blocks here, if you see them, like I can zoom in, they are showing like steps of our training. These NVTX ranges here. If I expand under CUDA hardware, so just to keep reiterating, this might look a little different on your screen. Like the CUDA hardware line might be like up top instead of below, but you can expand the kernels row and the memories row to see like what's happening on the GPU at the time. There's also an NVTX row that's showing what's happening compute wise. So the main thing I want to highlight in this view here is we've got step 10, step 11, which is where I've zoomed in. There's this big gap in between, which is just idle time on the GPU, which is it's due to data loading. We'll show you, we'll get into that. But for now, let's talk about what like the NVTX ranges we do see in the step are. So what we can see is there is at the beginning of the step, there are a couple of ranges that you can highlight over. There's data load or data copy in, forward. I don't know if people can. I can try and make this bigger, but I feel like that's a little better. There's
Yeah, Josh, just a sec, sorry.
Yeah.
What was your question?
Oh, I was just saying, could you like maybe cycle back and repeat what we're looking at?
I'd also like to maybe pause for a moment to make sure everybody is able to open Insight Systems so that they can follow along.
I was able to open it, open the inside, but I don't know how to open the file yet.
Okay, able to open it, but it shows an error.
oh, so there should be something like if you go File, Open at the top, then you can kind of pick. It's like double click.
Yeah, I know if you're on a Mac, you can also just like double click it, like you open your, Finder, double click on a file, and it knows that that's an Insight Systems file, so it'll launch Insight Systems. And that specific question about going back, can you clarify?
Oh, no, I was just like, which section of the run are we looking at? That was basically.
Oh, yeah, okay. Which section of the run are we looking at? Like how to understand where the top and bottom stuff is, or the annotations?
Yeah, okay, I see. It was just very zoomed in because I just was looking at my field of view and you can see all of it launches, but then I just wasn't able to map it onto what we were.
Okay, yeah, and it is very hard to see the words on Josh's screen. I don't know
Yeah,
what you can do about that.
it's one of
It's a
these
very busy
hard.
window. So, but that's why I think it's very important for everybody to be able to open this, to look at it themselves, so that you'll be able to get familiar with where things are.
Yeah.
Are there more folks who still need like help just getting it open and looking at a profile? A question in Zoom. How do we access this step 10 once you have the GUI open? I think if you're viewing the profile, Josh is just kind of zooming in. And there's
Yeah.
finding the NVTX row where you can see where it says something like step 10, but you can look at any step, right?
Yeah, you can look at any step. I mean, right now we're just trying to kind of familiarize people with what this like what the different sections of this window look like. And how to navigate. So I've been kind of just zooming in and out. So for folks that do have this open on a Mac, so basically you can drag your mouse across a certain section of time. So in this case, let's say I'm dragging this along like step 11 and 12. If you double click in the section that you highlighted, that'll actually zoom it in. So that's one way to zoom in. Another way that you can zoom in and out is on a Mac, it's Command. On a PC, it's Control. I'm pretty sure, but you hold Command or Control, and you can use like you can scroll. And so if you hold like Command and scroll in and out on a Mac, it'll zoom in and out. So these are kind of the navigational things that are useful. All right, so I'm gonna continue just talking about what we're seeing in this profile. Hopefully that'll work. That's okay. So the CPU section contains things like CUDA API calls and also its own set of NVTX ranges from like the perspective of the CPU. So what's included in the CUDA API row, which I've highlighted here, hopefully people can see it. If you zoom in, you'll basically see things like you can hover over. Like I'm going to zoom in like right at the beginning of step 11. You can see things like CUDA stream synchronizes. So like this is basically where the CPU is launched a CUDA stream synchronize and or you've called it, and this is waiting for the GPU to have completed something before the CPU is allowed to move on. So in this case, it's a CUDA stream synchronize after this hosted device memcopy down here. The forward pass is full of a lot of kernel launches. So if we actually zoom into like forward pass, I'm gonna zoom in like really close here. All these little blue blocks under CUDA API are like launches to kernels. So you can see things, I don't know, like this is gonna be really, really small in your view, I'm sorry. But if you hover over it on your own, you'll see things like call to name of a kernel. So element-wise kernel or point-wise kernel, some information about it like beginning and end and things like that. But the key distinction here is that what's being shown in the CUDA API row, and this is I think where people sometimes can get mixed up, is not actually what's happening on the GPU. So for example, I'm zoomed in here and I click on something called call to element-wise kernel. So like I can click on that. And if you click on an entry in the CUDA API row, it'll actually highlight what was launched on the GPU in the GPU row. So you can see here, I've got this like this little tiny CUDA API call, but down here, there's actually like a like a highlighted larger block. And so this is the CPU launching some kernel, but this is the actual kernel in like on the GPU that it ran. Hopefully that makes sense to people. So in this case, the CPU launched a kernel, at this point over here, and it queues it up onto the GPU, and at some point the GPU runs it. But the CPU, the thing with CUDA programming or in PyTorch programming is the CPU is running ahead of the GPU. The CPU is constantly like launching kernels that are going to be run in the future. And then so what ends up happening if I zoom out again is at some point, the CPU's launched all the kernels it needs to launch. Like it schedules them all to the GPU, and then it calls, it says, I need to wait for all those kernels to finish. And so that's what this giant CUDA stream synchronize is. Sorry, I'm just zooming out to step 11. So this giant CUDA stream synchronize is, okay, I've launched all the kernels that I needed to, forward pass, backward pass, optimizer. I'm waiting for the end, like all these kernels to complete. So if you notice that CUDA stream synchronize takes the entire like sequence of GPU kernel calls. So just to clear up, like this isn't that a CUDA stream, it's not that a CUDA stream synchronize took, 1.17 seconds. It's just, this is, what the CPU is doing, like it's spending its time doing. It's waiting for all these kernels to complete.
Okay, so I do see a couple of confused faces in the room.
Okay.
Maybe just like time to check in a little bit. I think just if folks could just maybe try to identify like the major sections here. If you have it open, right? I think one thing that can help you is can you find like this is where the CPU stuff is, where it says threads, or this is where it says CUDA hardware. Those are the CPU sections versus the GPU sections respectively. Right? Is everybody able to see that in their window? Okay, good.
I can see the CUDA stream synchronized.
CUDA stream synchronized. Yeah, can people find where it says CUDA
the
stream,
one
that big
bottom.
green bar? Sorry, what?
The one bottom.
The bottom?
It could be on the bottom, right? So like my view is going to be
Yeah.
inverted.
Right.
So
That's confusing, but like, there's a
Sorry.
setting to control whether the GPU stuff is on the top or on the bottom. So
Yeah.
when you open it, it might be the flip.
It'll be flipped. This is like the classic view. I'm sorry. I probably should change this before I do these demonstrations.
But, we did, but does anybody need help again, just like on how to open a file?
I just have a question.
Just a question?
Mhm.
Okay, do you want to go ahead and ask your question?
Yeah, what's the CPU block and then the threads block? I assume those are CPU threads.
Yeah, so basically each of these is actually a different CPU thread. So this first thread here, like you can actually see if, well, you probably can't read the text, but it actually says PT_main thread. So this is actually like the main PyTorch thread that's running. And so this whole thing here is like the main single CPU thread that's launching everything from PyTorch, more or less. So you can actually hover over these little yellow dashes below, and you actually can get some like call stack information from that. Like you'll see things like, oh, there's like a Python. Again, you can't read this because it's tiny on your screen, but you'll see things like Python 3.10, PyEval, some kind of function. So some kind of Python runtime stuff into like libtorch, into CUDA, like libtorch CUDA, into like libCUDA. So that's like, this is like the PyTorch thread. And so all these NVTX ranges and stuff are associated with that particular thread. So for multi-threaded workloads, like I can open these up. There's like a gazillion threads going on. I think a lot of these are like, we probably should do like OMP num threads equals 1. I think some of these are just like idling OpenMP threads, which we should like that PyTorch is also running. But for the most part, we can actually just ignore those. For multi-threaded workloads though, you might actually see some of the profiles we'll show later actually are multi-threaded, like the Dali, the ones that use Dali will have like other CPU threads with their own CUDA API sections and their own NVTX ranges to like show like that CPU thread, did this in CUDA, and here are the NVTX ranges on that thread. For this profiling example though, there's just one thread we care about, which is the PyTorch main thread, and then there's going to be like the one CUDA hardware section for the one GPU we're running on.
And then at the very top, there's like a CPU tab. CPU one, yeah, what is that?
This is just more I honestly don't look at it too much. It's like CPU utilization. So it just like shows you which CPUs are being used. So this is like the actual CPU hardware. The actual cores of the CPU you're looking at. So if you're kind of interested on what CPU is being used, like physical CPU core, like this shows that.
I
I
would look at this if like CPU compute is some bottleneck in some call or something, or with.
kind of I mean you can see the thread has this black bar which is also like CPU utilization. So I normally only worry about the threads. I suppose this could matter if you're like really oversubscribing your CPUs. But for the most part I consider like I look at the threads that are running my workload and then the GPU that's running and then kind of focus my view there. All right.
I have two NVTX. One is under CUDA hardware, one is under the threads. Can you see it again? What's the difference between two?
Oh, yeah.
So the NVTX range under threads, so under CPU is like the CPU perspective of the NVTX range. So and the GPU one is like the GPU view. And so what the difference is here, and actually this can be shown in this example if we look at forward. So if we see so again, this could be flipped over for you, but in the CUDA hardware section, I have a forward range that takes like 343 milliseconds, right? But if we look at this under threads, the forward range is actually this tiny blob here that takes like 9.6 milliseconds. So if I kind of scroll to the right, you can see that here's the forward on the CPU side, like on the CPU thread side, and here's the forward on the GPU thread, like GPU hardware side. And the difference here is that the forward marker on the CPU thread is how long the CPU took to launch all the kernels that were involved in forward. So the amount of time it took for the CPU thread to get from, push range, end range. But that doesn't actually consider how long these kernels took to run on the GPU. Because the CPU like schedules kernels to the GPU asynchronously. So the range under CUDA hardware is actually the one that you probably care about more, which is how long it took for all the kernels you launched within that forward range took to run. So in this case, this forward range under GPU hardware takes into account the time for all of these like the actual runtime of the kernel. So in this case, it's fuse, multi-head attention, and various like MLP related operations. So I hope that makes sense.
NVTX.
Oh, okay, now go.
So what you said NVTX and the thread is because it's asynchronization, so that the time they measured about the forward actually is not accurate. We need to see the CUDA hardware. That's the real forward time.
Yeah, so the CUDA hardware is kind of like the real
okay,
time it took.
right.
Yep. So I mean, this is kind of one of these like, if you're not used to CUDA programming mistakes people make sometimes where they go like, oh, I timed this giant kernel and it took like 10 microseconds. Wow, it's so fast. And it's like, oh, what you actually timed was the launch. Like the kernel itself is something different.
Right. Okay.
Yeah, that's an
Yeah.
important distinction. Okay, bunch more hands coming up. Are these questions for Josh or are they technical issues that we can help with?
For Josh.
Definitely Josh.
Okay, yeah, do we still have time, Josh, to go through more?
I kind of want to be able to at least hit a couple of the other profiles.
And then come back to these.
Okay, is that okay if we come back to your questions in a little bit?
Sure.
Yeah.
Okay, go ahead,
Yeah. Let's like move on a bit. So this is what like Nsight Systems gives you, and this is our like initial baseline case. So in this case, we've kind of synthetically made it look really bad as far as data loading goes by setting the number of data loading workers in PyTorch to 0. And so what this actually does is it fully synchronizes the data loading work. And so the highlight from this profile that I wanted to show is these are our training steps. So, step 11, step 12, but we see this like massive gap in between. We're like, what is that? And just by kind of knowing what the model is doing in this period of time, we know that this is like the data loader loading in a data sample, batching it and submitting it in. So basically we do step 10, the data loader synchronously is blocking everything. It loads data. And then the first thing you'll actually see at the beginning of every step are these little like greenish teal colored blocks here. These are actually the data copy in. So basically the CPU in this big white gap is loading data, the first thing that happens is this is the like data to like data copy into CUDA, like the data and the label. So these mem copies happen, and then forward pass happens, backwards pass happens, and then the optimizer happens, and then we wash, rinse, repeat. So if we go back to the training README, I kind of describe exactly what we're looking at in the README itself. But then the next thing we can go into after this is data loading optimizations. And so we've already made a lot of the data loading optimizations for you in the code under data loader, like adding these pin memory, persistent workers, and num workers arguments, which you can look at. So if you go into like the data loading, my goodness, the data loading file, which I think is in a subfolder here. Is it utils data loader.py? You'll see things like this is lines 36-ish in data loader.py. You'll see that we have like num workers is set to a parameter, which will let you control. We've got pin memory. I guess we're not actually using persistent workers, which is okay in this case because we're not actually running that many epics. But these are the couple of the options that we end up adding. But the one that we actually want to try first is num data workers, or adjusting num data workers. So you can actually run this command if you want. It allows, it basically lets you set num data workers to a value of your choice. I think the default we said was 0, which loads data sequentially, but by setting it greater than to the number greater than 0, it actually lets things happen using PyTorch multiprocessing with multiple workers in the background. So you can pick, you can run this however you want. You can run with 4 workers, 8 workers, 16 workers, and see the results that you get. We have some sample results here for 4 data workers, 8 data workers, and 16 data workers. I think we said that 4 was the fastest. So you can go ahead and copy and paste this command if you want and run it. If you want to go a little bit more efficiently as far as like the training goes or the tutorial goes, you can still add. So I'm just going to do like 4 here. Probably should have added this to the README. If you add the enable profiling and profile output arguments before it as well, that'll also run the profile. So we can do basically enable profiling equals 1, profiling output equals like 4 worker, something like that, and run it. But all we're doing here is basically taking our existing data loading pipeline and adding multiple workers. For time purposes, I'm just gonna again load up the profile that we already generated for this training, but you can feel free to mess around with it on your own. If we go to forworkers.nsysrep, we can see what that looks like. So I already have that downloaded on my computer and open. And hopefully you guys have that folder downloaded as well. And we'll kind of quickly go in through there, and then we can kind of take a break. But the key thing looking at this profile, so this is again the 4 workers nsysrep. We can zoom in here. We can see if I open up CUDA hardware and kernels, the major change here is that there's no gaps in between steps anymore. And this is because the data loading that was happening sequentially in the previous profile is now happening using these like asynchronous workers in the background. But that's kind of the main like aha of this particular profile. There are ways to actually show the sub processes. Because the workers respond using multiprocessing, they don't show up in the profile by default. There are ways to have them show up in the profiler. We didn't run the profile. We didn't run NSYS to do that, but in those cases, you'd actually see like a different CPU process with subnet VTX ranges showing like data loading happening in the background. but this is kind of like what you want to see in a profile once you have things sort of optimized data loading wise. For these for the large language models, because it's like text, or well, I guess this isn't text based, this is actually pretty serious like weather data, but it's not always as simple as adding num workers equal. Whoop, my Insight systems just crashed. Let's open that again. I got too many things open. Hold on. Open. Sorry for that. Go back. But the key thing is you want to see no gaps in the GPU performance, and that's for this particular case. It was easy just to add number of workers, and that happened. It's not always the case that it's this easy. So one particular reason why it's easy for this model, or at least in this particular configuration, is that the model itself is pretty expensive. So you can understand that if your data loading pipe, if your data load was taking like if it's basically a balance between how long your model actually takes to run, like forward and backward, versus how long it takes to load your data. So in this case, the data doesn't take that long to load. So just doing it in the background, it helps already. Like it basically gets us fully efficient in terms of like the CPU load being behind compute. But if you imagine you're in a different scenario where you're running a much smaller model or something a lot cheaper in terms of GPU compute, you might not get that lucky. Okay. So hopefully everybody can kind of play with this, but if we look at I'm going to go back to the terminal and we can see like the amount of time it took. These are all in the README, so I'm sorry for kind of not diving into these too far, but like we can see things like this took 41 seconds instead of 54. So that automatically saved us a bunch of time. Again, this was a bit synthetic because we made the data loader slow on purpose just for educational purposes. So let's go ahead and move on then to something a bit more interesting or something that might be a bit more complicated to think about. So I'm not actually going to run through the DALL-E example here because as I showed in that profile image, there's not really that much to gain here in terms of data loading efficiency, right? So we've seen that there's no more gaps. So any CPU data processing we've managed to hide completely behind GPU compute, fine. So the only thing that you can possibly benefit from or improve your data loading at this stage of optimization is this little section here at the beginning. So this section here at the beginning, these hosted device data copies, like I pointed out in the baseline profile, these are the copies of the data from the CPU to the GPU at the beginning of every forward pass, right? So there's that input.toCUDA, label.toCUDA at the beginning of our training loop. And so these take up, in this model, not that much time. In some models, again, if the model itself is small, or you're running on like an older model that's smaller or a much faster GPU, these could be a much more substantial amount of time. But we can see kind of out of this step, which I've highlighted in green, these mem copies are, I don't know, 2% of the time, something, right? Still, if you want to optimize one way, there are ways to do it. So what DALL-E does, I'm just going to show you a picture of what the profile does from the README, is DALL-E has a much more advanced like prefetching, or they've implemented sort of a data prefetch and a data like an asynchronous memcopy functionality for you that you just get out of the box by using it. So with DALL-E, you can look at the data loader DALL-E.py to see kind of fleshed out how you would use DALL-E for this example. I'm not going to go through it just for time, but if you look at the README and you look at what these so you can run with DALL-E. You can set data loader config equal DALL-E in your submit script using one of our submission scripts. What you'll actually see from DALL-E here is, maybe if I actually go to the profile a little bit easier to understand. So I'll actually do that. But what these images are showing is that those hosted device mem copies, those little teal blobs, are yeah, I'm going to open up the profile, are actually hidden. They operate concurrently with compute. So I'll just open that up really quickly just to show you, and then we can move on. So Dolly. Make this a little bigger. I'm just gonna really rapidly show you what's happening there. So we'll zoom into like step 11 or something like that. And so the difference here between the 4 workers using the PyTorch data loader and PyTorch is these hosted device mem copies that we saw were kind of happening sequentially before at the beginning of the step are actually hidden behind compute. And so the idea here is that these hosted device mem copies are happening in step like n-1 for the next step. So these 2 like mem copies here in step 11, these 2 teal blobs are actually loading data that is supposed to be ingested by step 12. And so there's no blocking anymore. Minor optimization, right? But still, could be useful depending on your use case. So that's why we show it here. One thing that we can also show for somebody who was asking about threads earlier is this example. So if I keep expanding the threads, eventually we actually find that Dolly has some threads that it's running. I don't know how well you can see what's going on here, but there's like a Dolly thread here and a Dolly thread here that I've got highlighted. And the Dolly threads themselves actually have some markers in them that show what Dolly is doing on the CPU. So for instance, if we zoom in to this thread here, we can see like, oh, there's a Dolly executor run CPU. It's running some external source operation, which is reading from an HDF5 file, I think. This Dolly thread here, if we zoom in, it'll have things like it's running on the GPU, it's doing like a normalize operation, and here's a bunch of CUDA API calls that Dolly is running. What are these? These look like some kind of async mem copies and other kernels, which we can also see if we like look in. You'd actually see them in different like CUDA GPU hardware sections, or you'd see like, oh, like vectorized. Not sure where those. There'll be some Dolly kernels here. Actually, I'm not sure. Yeah. So for example, we see this like underneath our compute. Sorry, probably this is very hard to see for people, but if we're back in like step 11, we zoom in, we'll actually see that there's some other kernels that are getting launched concurrently with the compute, like normalized inverse standard deviation kernels. So these are Dolly kernels that are doing some kind of data augmentation. Okay. So going back to the README, just because we're not running these cases, what we actually see if you look at the README is that Dolly doesn't really provide much benefit in this case, just because, as I pointed out, the only benefit we would get from Dolly in this scenario, in this model, is asynchronous host device mem copy. So at least according to the README, we go from, what is it, like 41, like our, let's see, we did 4 data workers, was like 40 seconds per epoch to, with Dolly, like a 38. Okay. So that's all on data loader. So we'll spend the last 15 minutes, and I guess there is like some time afterwards to talk about mixed precision training. So again, so the way that we've done this tutorial is we've just sort of set things up for you by adding arguments to the submit PM script. This first section I won't go over, but this is actually showing the benefit you get from using TF32 on NVIDIA GPU. So TF32, like I said, is this like kind of halfway in between compute format between FP32 and FP16 that's actually automatically enabled on A100 and newer GPUs. So what this example here is showing is if you disable TF32 via this flag, which you should probably never do, this is kind of just a debug flag, it shows you how much benefit we got from TF32 in the first place. So if we turn off TF32 using this flag, our epoch time goes up to like 50 seconds. Right, so we see just by default, by using like an A100 GPU with TensorFlow TF32 support, we go, from 50 seconds to 38 seconds. right? But that we can do better by actually explicitly enabling mixed precision by using AMP on Perlmutter. So you would add this AMP mode FP16 or bfloat16 to the submission script to see how that works. If you want to look in the code though, basically you can look in train.py, and I used to have like some comments that label these things, but basically you can just search for things like AMP. Actually we should look up like AutoCast. And you can see where we've added AutoCast with AutoCast CUDA. Sorry that the font's probably kind of hard to read, but let me close this folder. With AutoCast CUDA, what params, if you want to enable it, this is true or false, what D type you want to run. So these are just config arguments in the YAML file to this model. You've wrapped in this case, we've wrapped the model, like the forward pass and the loss calculation in AutoCast. And then again, like as I showed in the slides, if you're running in FP16, you need to use this grad scalar object, scalar.scale loss backwards. If you're not using FP16, you just do a normal loss. Okay. And what we actually see is if we enable FP16, actually we'll go to BF16 because I think that's the fastest one. That just those lines that do the auto scaling or AutoCast drops the epic time to under 10 seconds. So about 9.5 seconds per epic, which is like a pretty big improvement just for a single, a few lines of code. We can go ahead and run that one if you want by copying and pasting this line here for BF16 precision. Like I can submit that myself. But again, you can go in and look at the files and see what's going on and play around with them. There's not a lot of time obviously during like the hands-on while we're going over this directly to mess around with it as much, but we've tried to leave things as standalone as possible in the repository so that when you do have time, you can look more deeply at this stuff. So if you add the profile stuff before this, you can also profile this run. So I'll just like tail it. Well, it's still going to take a while to run, but again, I'm just going to kind of skip past and show you. Well, actually, before I load up another profile, we'll just go through the kind of the final setup updates. So that's mixed precision. So with mixed precision with bfloat16, it got us down to around 9.5 seconds. And then the last set of sort of miscellaneous optimizations we've added are torch just like JIT compilation via torch compile and fused optimizers. So I mentioned fused optimizers in the last slide of the presentation. This is also not super beneficial here, but basically the idea is normal PyTorch optimizers run a kernel on a per parameter basis to update the weights. Fused fuses that into a single kernel, which is more efficient, or single or a few larger kernels to make that more efficient. And I think the other optimizations were torch compile. But what we actually find for this model, again, because it's really just dominated by like the gems and like the transformer, that these types of small optimizations of like the optimizer and the loss function that get compiled, it's not a huge gain. So actually we see that it's basically the same speed with the fused optimizer and AMP enabled. You can try this out. Actually, it looks like my it kind of gets a little faster, 9.3 seconds. If you add basically -- enable fuse -- enable JIT to the submission script, it'll run with all those optimizations. And so the final profile that kind of contains all those optimizations we've already posted for you in that sample NSYS profiles folder. Dali, AMP, bfloat16, fuse, JIT, NSYS rep. Really creative name, which you can load in your own Insight Systems. And kind of see the kind of optimized model, at least optimized through the mechanisms we've shown, kind of in all of its glory. But like I said, with these transformer-based models, when we're spending so much time doing compute here, there's not as much to be gained by like these fused JIT kernels. But still, the major performance optimization in this case is just to optimize the compute, which is enabling mixed precision. Yeah, let me see. I'm pretty sure. Yeah. That's kind of interesting in this case. There's a lot of multi-tensor apply kernels, but anyway, that's the end of the hands-on section, or at least we got about 7 minutes until the top of the hour for people to ask questions or play around with things. But I guess the kind of the punchline here is that we went from our unoptimized model, which took like something on the order of 54 seconds per epoch, down to the fully optimized model on a single GPU taking about 9.5 seconds, which is a pretty big speed up for not too many line changes.
Great. So that's like a factor of 5 speed up that you can get just by focusing on the single GPU performance. Everybody, that's important. I hope you realize that.
Yeah, and while while we're looking currently at this vision transformer model where some of these, adding the fuse optimizers or using JIT, didn't seem to have that much of an impact at the end. The previous version of this tutorial where we're running kind of a more I shouldn't use more conventional, but like a different, like a CNN type model, maybe a more old school deep learning model. These make a much bigger difference. So really, like, just because this particular example is not showing that these features have like a huge effect, don't assume that they're not useful. It all depends on context.
CNNs are now old school.
Everything, yeah, deep learning moves fast.
Yeah. Just a quick heads up. So, this session with Josh ends at noon. I don't know if you have to leave immediately after that, but we're certainly going to be around here. People will be able to keep running things for a bit. Basically, we just kind of decide to end when we think we're done here. I think the schedule goes till 1, but we're probably all getting hungry too and want lunch. Well, there's still breakfast burritos for those in the room.
They should ship me one.
And
Also, the training accounts will go tonight, so people can follow, catch up on the tutorial and ask questions.
yeah, the Slack will still be there. The reservation will end at like 2 p.m. though. You can still run outside of that, but you would have to remove the reservation argument in the scripts to do that. If you need help with that, you can always post on the Slack. Any questions for Josh though, maybe before we? Yes.
So when I'm comparing the Nsight thread viewer for the baseline versus the 4 workers, I think I'm missing something. I see these gaps between the different steps. And that's, supposedly because of the longer data loading, but I don't see which block is actually active at that time. Like I just see gaps in the baseline group.
Yeah, so this is like the one question that comes up a lot in this tutorial is that, how do we know that this gap is data loading? There's a way, like we didn't actually, if we look at this code and we look at the NVTX markers that we've added, sorry, this is like, and we look at the PyTorch training loop, we can kind of deduce that this is data loading. It's just annoying to actually show you that in NVTX range. And the reason is this, if I go back to the actual code, like we could have made the code like super ugly and made this more obvious, but man, all my terminals are
Still
like,
can't control C anything.
okay, hold on, let me go.
Just X out the terminal.
That doesn't matter. Okay, so I'm just gonna, because this is like, it's actually sort of annoying. So the reason why we haven't, like, you don't see like the data loading part with an NVTX range is because all of that like CPU data loading, at least in this case, when we're not using multiple workers, is happening inside the like Python get next item thing in this loop. And so we haven't broken apart the iterator to say to add a range around what's happening when you call this, like when you like call the next function on this generator, if that makes sense. So all of this white space in the profile is what's happening inside the call to like get next of train data loader. We could have added an NVTX range that would show you it on the profile explicitly that that's the data loading happening by kind of exploding this data loader by like calling next, basically having this be like a for loop from I equals like, length of data, like 0 to length of data loader, and then calling next manually, and but then it makes the code super ugly. The other way of doing it, and I guess that we could have done it, is inside the data loader itself. Like in the data set, you can add NVTX ranges, but like it's sometimes those don't show up because they're launched by different processes. But anyway, so based on kind of the deduction of where these NVTX ranges are. So step 14, for example, if I go back to Vim train and I say like the step range starts here so basically we have a for loop. This stuff doesn't matter. We have a step, we push the step here at the beginning of the loop. We pop the step range, like the step range off at the end of the loop. There's like an LR schedule versus a CPU step. So I guess technically this could have taken a lot of time, but it doesn't. We should have cleaned that up a bit. But assume this step was like all the way at the end. If we know that that step range kind of captures everything that's happening inside this loop, the only thing that can be happening in between the steps is whatever's happening inside train data loader, if that makes some sense. And so that's like how we sort of deduce in this case that this is all just what's happening in between loop counts, which happens to be data loading.
Okay, a few other hands have been up in the room. Hopefully we have time. I think both of you guys had questions, right? Whatever order. I don't know who was first. Okay, you go first.
Okay, yeah, I was wondering how, after I've trained my model, how these strategies apply to like just running inference. Maybe how that changes, like, because I think like running, obviously on transformers, the consideration is getting like quick inference time as well.
Right. So this is like mostly training focused. I mean, so for inference, things like lower precision helps, but I mean, you would have trained your model in that precision in the first place. So kind of the inference you end up having of a model that you trained sort of depends on how you trained it, right? Because you sort of you have to train it at the precision you're running at. You can do some other stuff after inference to reduce the precision or like distill and do all this other stuff, but that's kind of a separate topic altogether. So this is more for accelerating training of these models.
But a lot of the stuff, I guess, still kind of carries over, right, Josh? I mean, you can still.
Yeah. So like some of the like
Torch
the mixed
compile.
precision stuff, the torch compile. Torch compile is actually probably the biggest thing for inference, right? So if you're really actually, so let me take it back. So there is some content in this that is relevant to inference. For one, so torch compile is a big one. CUDA graphs is also a huge one for inference, right? Because for inference, you're usually really, really sensitive to latencies, and so CUDA graphs and anything you can do to reduce latency is the big thing. So using CUDA graphs, using torch compile, using CUDA graphs via torch compile, but then beyond that, there are other tools that people use to accelerate inference outside PyTorch, like TensorRT or like TRT LLM, which kind of compile these models down even further into like more optimized kernels for inference after you've trained them.
Okay, next one.
Which part in the profile is the one for the choice time convolution?
Did you hear that, Josh?
I can catch it.
He's just asking kind of where in the profile you can see just-in-time compilation. I mean,
So
the actual compiling is what
No,
you're.
it's like the difference, like.
Oh, the difference. Well, yeah.
so in this model, it's not gonna be. It's like hard to. You'd have to look for. It's gonna be in the loss somewhere in here, but where is it? I guess the loss is gonna be somewhere at the beginning of forward. Oops. Or somewhere here. This I can actually find it. I'm not actually sure how much of this stuff gets compiled anyway, because a lot of it's not pointwise fusion. I mean, you basically have to dig through here. Like, there's actually not a lot that got compiled. But what you would look for is basically things like, if I brought up the slideshow, there's like weird kernel names that the original PyTorch JIT compilation would basically create these weird names like mul pow pow mul sub add like kernel or something. These days there's just kernels like Triton something or another. Shashank, you might wanna, I can't remember, do you know if like there was any like visible JIT compilation that even happened in the final version that got added? I don't,
Yeah, you should be able to find some Triton kernels. I think I thought.
it's like some Cutlass stuff.
Some with Triton in the name.
I actually don't see any in the profiles run, so I'm curious if maybe JIT wasn't run on this particular file that I generated. So it's possible that this kernel actually didn't even have, this profile doesn't have Triton added. But what you would do though is you can go through this kernel listing and it lists like every single kernel that got run by name. And you would look for basically kernels with like Triton in the name, and that would be a compiled one. It looks like there's actually not anything compiled in this particular one though.
I think the example doesn't, but people should have it in their profiles.
The example, you mean like the one that we
It's from
pre-generated?
last year, basically, but
Oh, okay. I wasn't sure if you updated the profiles after because so we did have an issue where like the compile wasn't working correctly. I think when we generated these profiles, but Shashank could fix that. So the profiles that you generate, if you generate some fresh ones on Perlmutter, should have some Triton kernels in there.
Josh, do you need to leave?
I can stick around for a short period of time, or at least be like checking the Slack.
Right, okay, yeah, let's get through a few more questions then. Ree?
So thank you, Josh. Where should I find the Dali prefetch operation using the NSAT system? Because right now I can only see a very short set data source operation. I don't know where to find the prefetch.
Oh, the prefetch operation. So it's like, let's see. So we're looking at the Dali one, right? So it's like you'd have to basically dig through these threads, but you'd see something like this thread here. So I'm in the thread section, and so as I mentioned before, Dali uses CPU threads, not multi-process. So we can see those CPU threads in this profile. And what we can actually see here is, sorry, it's like really hard to get the view right. So this is step 12, right? Like this section here. So let's kind of zoom in. And we see that there's these memcopy kernels happening at some point, but they're getting launched by something. And actually what we're seeing is this thread here is the one that's launching these memcopies. So there's this Dali. The CPU op is actually loading the data from the CPU. So these external source 1, external source 0, this is loading the input and the label from the CPU. So you can see that this is like Dali executor run CPU. And then that's this thread 1063998. But this other thread up here is the one that is on the GPU that's responding after the data is loaded from the CPU pipeline. Dali has this executor here. There's like, it looks like there's two different, there's like a mixed operator and this run GPU one, but the mixed operator here is the one that I think is doing the CUDA mem copies. So if you zoom in to that one, you can see some like Dali mixed op, which is like a CPU GPU op. Copy CPU to GPU, external source 1, copy CPU to GPU, external source 0. These are what are launching these host device mem copies. Like, I think that might answer your question, but basically these are the Dali threads that are busy doing the work in the background. And so
we go through all the threads to find this prefetch.
Yeah, so like Dali does label a thread. So if you just kind of open up the threads, you'll find the Dali ones. But it looks like in this case, there's 3 of them. There's a thread that runs CPU-based ops. There's a thread that runs mixed ops, which are ones that involve the CPU and the GPU. So the mem copy here is like a mixed op because it's copying from CPU to GPU. And then there's this other thread here, which is like the GPU thread. And this is the thread that's busy launching like augmentation operations on the GPU. So this normalize inverse standard deviation kernel is what's getting it's getting applied to the GPU buffer that DALL-E is loaded. So if I like click on that API launch and I zoom out,
All right, thank you.
yeah, so it's all there. And then if you look at the the data loader DALL-E code, you can see where the pipeline is generated that sets up this whole thing. But ultimately, DALL-E works kind of like TensorFlow or PyTorch would, where you set up this kind of pipeline graph that has input output dependencies, and it just runs through them.
Okay, do you have time for one more question?
Yeah.
Go ahead.
Thank you. I have a question about how you can use Nsight systems to profile code that's like not using Python to interface with GPUs. Like maybe you're having a C program, you're like uploading GPUs as well. Like, are there pragmas for that? Like, how we go and learn how to get the
Oh, I mean, so basically, like if you're profiling like a C, like a code, like a C++ code or Fortran code, something that you actually are in control of, like Nsight is even more powerful because you're not limited to what PyTorch has exposed. So you could literally do the same. If I go to like the terminal, and so if you extract from the submission script, submit.
You probably have other training events too that cover that sort of stuff.
Yeah, there's plenty of, there's actually some, I should probably find a link and I'll post it in the Slack, but there's like a lot of Nsight examples for just regular, non-Python, non-PyTorch, non-DL programs. But this call, nsys profile -o, these different trace arguments, followed by your CPU, like your binary for the program that you ran, will generate a profile just like this.
Oh.
Like Nsight is not specific to Python at all. Really, we're running PyTorch through Nsight, but Nsight is just seeing it as like any old program, and it's just recording what's going on. And so you can run Nsight on any binary that you generated that doesn't even use GPU actually. You can it might not show anything that useful, but and all of this stuff, the kernels, memcopies, streams, they'll all be there. And then there's like NVTX itself is like a C++ header and has functionality to push and pop ranges and do all kinds of stuff. And you can do all of this and more if you do this in like C++ or Fortran or C.
Great. All right. Thanks a lot, Josh.
Cool. Yeah.